All right, so recording has started, and as with the last exam, we are going to um, go through the notes and just do a quick summary of things, say what is maybe more important to study, what's not, and then do practice problems. But before I do any of that, I want to say a couple logistical things for the exam is one, it's on Tuesday, which is, hopefully that was not a surprise. But you can still bring a cheat sheet, and it will be similar in structure to the first exam as far as whether I say no work required or there is work. And there will be a bonus and kind of all the usual stuff on that. The only new thing I want to add is about the cheat sheet to maybe help you in putting yours together. I'm going to make some suggestions, and that would be, for one, that since you're already given all of the equations, and they will be these ones that are on the practice exam, this will be what you're given. At worst case scenarios, I add a few just because I think, oh, it may help for them to have those as well. But if I don't, which already I see that I should add the ones for resistance, so I'll do that. Series and parallel, unless I'm missing it somewhere. 1 plus R2 plus blah, 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 if they're in series, and resistance in parallel, 1 over R1 plus 1 over R2 plus blah, blah, blah. So I'll add those to this, and if I realize that I missed any other major equations that you would need, I will add those. But I won't take any off. So for your cheat sheet, what you want to do is not write down a whole lot of extra equations because you realize for one particular problem, maybe we wrote it a slightly different way and you should add that equation or something. Instead, you should be kind of making sure that you understand what each of these equations is saying. And on your cheat sheet, you could put something like, first equation about the C parallel plate says something about the capacitance of a parallel plate capacitor. For the bottom few, it's talking about charging and discharging the capacitor. So that way you don't just see a bunch of symbols here, you know when those symbols are relevant, what types of problems it might be relevant to use these equations for. The other thing is a lot of people will go straight to putting a bunch of examples, looking back through the notes and listing all those examples, or going through the homeworks, listing a bunch of those problems or whatever. The trap there is that you start to think, if it's not exactly like that problem, you're just going to get completely lost. And so it's better to not focus on specific examples where you are trying to hunt for a certain thing and see if it'll work for the problem we're trying to solve on the exam. Instead, it's better to just know how problems are solved. So by that, I mean, if you see a picture of a circuit in the problem, it's probably likely that you'll be using something like junction rules, loop rule, or series and parallel, that kind of thing. And that narrows down what you would do to solve those types of problems. If it is resistors in series and parallel, you know that what you need to do is simplify the circuit down to one single resistor using series and parallel rules. And then you need to say, okay, I work my way back up that chain of harder and harder circuits until I get back to the original by saying the voltage is the same for any resistors in parallel, and then using Ohm's law for the other piece, or the V equals IR for the other piece. And for any that are in series, you need to say current's the same, and then use V equals IR to get to the voltage. So it's more important to know what process you should follow to solve a problem than a specific example of that problem. But if you can fit both, list the process and have a little tiny example of it, that's a good idea too. I just don't think you should fill up your cheat sheet with a bunch of formulas and a bunch of examples, because if you do that, you're going to spend your whole time on the exam just looking for something on your cheat sheet rather than just getting a quick reminder of how to start a problem, which is what it should do for you. Okay, so with that, let us go ahead and recap some things from the notes. So, chapter 25 on capacitance. On this page, the biggest thing is just how capacitance relates to charge and voltage. It says, if I have a certain charge on my capacitor plates, the voltage across those, or the potential difference across those plates, is determined by this capacitance. So if I have a capacitance of 1 farad, then when I have 1 coulomb of charge on my capacitor plates, meaning positive 1 on one side and negative 1 on the other, I have a 1 volt potential difference across them. If I have a higher capacitance, that means I can have that 1 coulomb of charge stored at a lower potential difference. If I had a 2 farad capacitance and was putting 1 coulomb of charge on the plates, I would only have a half volt potential difference. Yes, Hannah.
Professor, just a small clarification. So the capacitance only depends on the
Capacitance only depends on, I didn't hear the last part. Could you repeat that? Okay, I'm not hearing you, but
I'm so sorry.
this may answer.
Can you hear me now?
Yes.
So the capacitance only depends on 3 things, right? The dielectric, the distance between the plates, and the area of the plates.
Yes. If we're being
So
strict, it's a parallel plate capacitor only depends on those things. For a spherical or cylindrical capacitor, it's very similar types of things, but it would be, radii instead of maybe exactly the distance sometimes.
So even though we have this equation Q equals CV, Q and V don't have any influence on the capacitance, right?
That's exactly it. C is itself a function of those other 3 things. So here. So
thank you.
capacitance is a function of these 3 things, but then it can be used to relate charge and voltage. It doesn't itself depend on them. Like with this water tower thing, the capacity of the water tower is area, and its geometric properties relates the mass of water to how high up it goes, but it is not dependent on either of those things. It is dependent on those geometric properties of the water tower. Okay, so that is important. It is a geometric property, does not depend on C or V, and that's restated here. And then we add in the dielectric later, so we'll put that later. Units, it's important that it's farads. I don't know why it loses its mind as I'm doing this, but anyway. Farads, but you may see microfarads on the exam. That's 10 to the negative 6 farads. So if you see micro, just remember that conversion. It can also show up with coulombs because you don't ever see a whole coulomb charge just sitting anywhere unless it is something very dangerous. Okay, this next bit is not super critical, even that last formula, in the sense that we're going to update it later with that dielectric constant. So this formula is going to be improved in a sense by accounting for if we put a dielectric between the parallel plates. So this part is not super important, but these, just knowing what's what here is, because the equation sheet does not tell you anything about these pictures, does not give like what A is, what B is, so it might be good to make sure you know. The formulas are given, just not, what's what in it. The dielectrics, the important thing about dielectrics is that they weaken the electric field between the plates of a capacitor by becoming polarized on their surface. And the amount that the field is weakened by is this dielectric constant, but usually it is a given quantity. It depends on the material. In the case that you're dealing with vacuum, so empty space, or air, that dielectric constant is, for all practical purposes, just 1, and so doesn't affect your calculation of capacitance. If you're given another material, it will probably tell you on the exam that kappa equals a certain number, and then you would use that in your calculation of capacitance. And we know that in order to do that, if, say, we're looking at a cylindrical capacitor, this does not have kappa in it. all we have to do is replace epsilon zero with kappa epsilon zero. Similar here, and then similar here, and also for the parallel plate capacitor, but that actually gets written out explicitly a little bit later.
So I had a question.
Yes.
So on the homework, it had to where we had to solve for K. So you saying on the exam that you automatically give us K?
The only case in which you would solve for it would be that everything else around it is given in something like C equals kappa epsilon zero A over D. And so if everything else is given, I think it's fair to ask about that, but that's probably not what I would ask for. So let's say most likely no. Okay, so the one we do need to worry about for parallel plates is where we already account for that dielectric constant, so that right there. We don't need to worry about how we got to that formula as far as the exam is concerned, but right, exams are not all of what physics is, so just keep that in mind. We're not crossing these out as far as it's not important, it's just not going to help you for the exam. So these kind of questions are pretty likely as a conceptual type question. So if you keep either the electric potential or the charge the same, and then change the capacitance by changing the dielectric that's present in your capacitor, then what happens as far as charge, electric potential difference, and capacitance? So if you have a dielectric and you have not put it in your capacitor yet, that capacitor has a certain capacitance to it. When you slide that dielectric in, it's going to increase that capacitance. Depending on whether the charge across the capacitor is fixed or the voltage across it is fixed, that will change something and keep something the same. If the charge is kept constant by keeping the capacitor isolated so the charge has nowhere to go, and then you insert a dielectric, then the charge can't change, but the voltage does as a result of you increasing that capacitance. And that's what this first example is about. It says that the voltage is decreased. The capacitor gets better at holding on to that charge. It takes less energy to do it. Okay, if you have the voltage fixed because you've got a battery connected, then the charge can change because more can flow from the battery or to it, but the voltage itself cannot change. And that's what this formula says. It says inserting that dielectric increases the charge on the plates, even though with the battery connected, it does not change the voltage across the capacitor. But that would be like a no work required multiple choice type question. It's what happens. This example tells you how to calculate capacitance with a dielectric. So it's just an example of calculating capacitance. That is a good thing to know. These ones are not very important, but the idea of replacing epsilon zero with kappa epsilon zero, if you've got a dielectric, we already saw is important for calculating capacitance correctly. Series and parallel, it's all summarized in these boxes down at the bottom of each page. They tell you everything that's important about series connections, in that the charge is the same for capacitors in series, the potential difference is split, and the equivalent capacitance formula, and similar for parallel. Yes, Emma.
Professor, could you please once again go over how to distinguish between series and parallel connections in circuits?
Sure. So series, I always look at as, do I only have one path from one capacitor to the other? So if I go to something where it's definitely not series, like this parallel one, the reason I know it's not series is because this C1, I can get to C2 by going around, or I have this other path, or I could go through this branch. I've got a lot of different ways that I can get from C1 to C2, and that means charge has a lot of different ways they can get from one to the other. There's not one single path. If they're in series, or you could go the other way around the loop, sure, but there's not like a branching path. You could go one way or the other way, there's only that kind of one pipeline for charge to flow through. And parallel, you recognize as that kind of branching idea, but it's a specific thing about the branching. It's that I look at my top capacitor, I say, okay, the left side of it, we can think of as like a very long leg that the capacitor has. Same for the right side. If that is all that's in between that capacitor and the other capacitor, meaning I can draw legs for this one down here, C2, or I guess I'm calling this C1 too. And that's all that's between them, those are in parallel. If it's not one of those two things, it is not series or parallel. So series, look for whether there's branching paths. If there's not, you have series. If it's parallel, you can have branching paths, but only this specific type of having the two legs in common on either side. Okay,
I know I'm going ahead, but when we have resistors instead of these capacitances, so instead of using this series or parallel convention, can we almost all the time use the Kirchhoff laws to calculate the values just to be sure?
absolutely, you can. If you
Okay.
don't like series and parallel, you can always do Kirchhoff rules for everything. It's just, if we have series and parallel, it can be a little bit shorter sometimes, but if Kirchhoff rules are more comfortable, absolutely do that. Don't even ever worry about series and parallel.
Thank you.
Yep. Okay, so that's series and parallel capacitance, and this is an example of that idea of taking your more complicated circuit and simplifying down until you get a circuit that only has one single capacitor and the battery. And with that, you work your way back up using these series and parallel relationships. So that is a good example. Anything that says application through this whole set of notes is good. You want to know the applications of these things, but it's not going to help you for the exam. Similar here, so energy stored, we got 3 ways we can calculate it. All of them are equally correct. It's just some are less confusing to use. So by that I mean, all right, we look at where we've got a change in capacitance. Say we change the capacitance by inserting a dielectric in between the capacitance. There's that question of, does that raise the capacitance? Because this one, or I'm sorry, does that raise the energy stored in the capacitor? Because it looks like that's what this one is saying. Or does it lower it? Because it looks like that one right there is saying that it lowers the energy. To answer the question, we have to know about those other two things, the charge or the potential difference. And if we're keeping one fixed, that it's that idea of you have a battery connected or you have an isolated capacitor where the charge has to stay fixed, then that tells you something about what's constant and what changes. If you have a battery, you have a fixed potential difference V, you probably want to use this one because it doesn't depend on the other thing that changes, which is the charge on the plates as you insert a dielectric. If you have a fixed charge, you have an isolated capacitor, you probably want to use this one because it only depends on that fixed charge and this capacitance whose value changes. The voltage also changes, also depends on the fact that you've inserted this dielectric, and that just complicates things because it ends up with you having 2 variables to deal with in every other version of this formula except this one. Okay, that's the main things for that page. So how we got to that is not as critical, but a calculation like this is a good one to look at. It's more likely that it'll be like you have a circuit with series and parallel capacitors, and you want to know what the energy stored in a certain one of them is. To do that, you just have to look at that certain one, and if from previous steps you already know the voltage across it and the charge stored on it, that's pretty easy to do. You could use any one of those formulas. It's more for conceptual type questions that it helps to use one or the other to guide you, because the conceptual questions will say keep the battery attached, and so you fix the voltage, or you keep the capacitor isolated and fix the charge. Okay, chapter 26. So we looked at things on two different scales. And I'm just going to try and quickly get through this one to say what is most critical. So current density, the main things I would ask for current density have to do with how it relates to drift velocity and the charge carrier density. That's what this NE thing is. It's the amount of free charge per unit volume. They call that charge carrier density, but it's just how much charge is in a certain volume of material. And then how that current density relates to current, which I'm only concerned about this kind of special case of if it is uniform current density. In that case, current is just that current density multiplied by the area over which that current density is flowing through. Otherwise, it's things like this, just directions for stuff. So yes, hang on.
Do we have to know the proportionalities between like the electric field and the current density, like if they're directly proportional or not?
So electric field and current density. So the relationship there would be the resistivity, but I haven't pushed for that particular relationship very much in homeworks and quizzes. I haven't tested on it very much, so I don't think it's fair to test on it here. So if I look at that part where I talk about it, that would say that this thing is pretty much out as far as something I would ask about.
Moreover, Professor, so the current density is always going to be in the direction of the electric field for positive charges, right?
Yes, because it is the direction positive charge would flow as a result of that electric field.
So can we say that for almost all cases, if we are given the direction of the electric field, then that's the direction of the current, or do we need to look at what material is given to us?
So that is a safe bet because what otherwise is that this thing resistivity is negative, and there are materials that have that, I believe. It's like they're designer materials. They're specifically designed to have these very odd properties, and that's not something I'm concerned about. So you could have given the direction of one, that is the direction of the other.
Thank you.
Yes. Okay, so we don't need to worry about the integral form of the relationship between current and charge density. We do need to know that charge is related to that current through, for what we're concerned with, more or less a ratio. If you have a constant current, that's just charge per time. We don't have to worry about derivatives because if it's constant, it's the same value over all time. And that means also integral stuff here is not as critical, but this part is.
I had a question.
Yes.
Why did it switch directions when it went from the positive to the negative, though?
So this
Their
example,
potential, I guess.
are we talking about this example or are we talking about a different one?
That one and the one above it.
Okay, so yeah, let's start with the one above just to recap. So for this one, we're talking about positive charge moving. And so the drift velocity is always just what direction is charge actually moving. It is the one that is the way you think it is. So drift velocity is to the right because the charge is moving to the right. Now, because the charge is positive, if we see it moving to the right, it must be that it was an electric field pointing to the right to make it move that way. And then that says that the current density is to the right because we say it's the direction an electric field would move positive charges. So it is to the right. Now we go to the negative charge. It's moving to the left. So drift velocity is to the left. That's the way the charge is actually moving. But because of we already had this convention for electric fields of they're based on positive test charges, the electric field is opposite the direction the charge moves because negative charges field forces opposite the direction of the electric field. And that also means the current density is opposite the direction the charge is actually moving, because it is defined based on this convention in terms of positive charge.
And this is with or without the EMF?
So an EMF would be another way of looking at what causes this flow of charge because of this relationship between electric field and potential difference. In a region where something has an EMF, where it is doing work on charge, it has a certain electric field. The EMF is doing work to raise something to a higher potential against the electric field. So it factors in, but because that's EMF is not introduced until the next chapter, I'm not trying to do too much like interdisciplinary or inter-chapter stuff. So it would not ask a question like this based on EMF.
Okay, yeah, because that's what's confusing me. I feel like.
Yeah. So we'll get to how it relates in the next chapter, but as far as a question like this, it's not that's not something I'm looking for. Okay, so that's I think the main things here. The derivation stuff was not super important, other than I don't know that I'd even call this a unique or new equation, because it's just saying that speed is distance over time. But it could help you in questions like are on the exam review about how long does it take for charge to get through a certain circuit, to get to a light bulb from a battery, or to get to the starter motor from your battery in your car, things like that. So these two equations are the kind of relevant ones for that piece. All right. Conventional current is this thing of we pretend positive charge moves one way, because we already messed ourselves up so much with all these things defined in terms of positive charge that we might as well just start pretending it actually is positive charge moving when we're talking about circuits. And so the rest of this is just justifying that that's okay to do. The main thing to remember is just that conventional current is always going opposite the direction that electrons are actually moving. So if something asks you about conventional current or just says current, that's kind of implying conventional. We're talking about the pretend positive charge motion. If it's asking about the direction electrons move, that is opposite. And that's related to this stuff up here in this example of electrons do kind of the opposite of everything else. So the thing for resistivity that's probably most relevant is this sort of relationship, how it depends on temperature. And there's an example for that right here. You would be given the coefficients you need, the coefficient of thermal or temperature coefficient of resistivity, alpha, and you would be given the reference resistivity. You would not be pulling from an actual table. You'd be given enough values to just kind of plug and chug. Okay, resistance, how it relates to resistivity is important. So in the chat, it's very difficult to solve. Problem 46 in exam 2 review, and explain how to determine which resistors are in series and so series and parallel resistors, it's exactly the same as what I said for capacitors. Series and parallel capacitors. Is there more than one branch between them? If not, it's series. If there is more than one branch, you have to check if the two sides of each component are connected through just wire. There's nothing else in between. And how to set up the problem for using Kirchhoff cells. Okay, all right, so when we get to that stuff, we'll talk about that. So, make a note on 46. For resistance, how it depends on resistivity is this formula right here. The stuff above is just trying to conceptualize that for you. So if that didn't help any, you don't have to worry about it. If it helps you understand this relationship better, then by all means. Ohm's law, big thing about it is that it is just saying resistance is a constant. And it's not true for all materials, it's true for ones where it's true, just based on experiments. If you apply a certain voltage, you measure current, you keep doing that for different values of voltage, and you find that current increases proportionally so that the ratio of the two, this slope, is constant. That is a material or a specific conductor that obeys Ohm's law. If the curve doesn't look like that, if the relationship between voltage and resistance is something more like that, maybe, red curve, then we call that a non-ohmic material. It does not obey Ohm's law, which is why it's kind of misleading to call it a law. It's not like a law of physics where we expect it to always be true. And so calculations like these are good for calculation-based stuff. And power, I mean, you don't have to worry so much about how we get to this formula, but what it is in general is power is current times voltage. And what it is specifically for resistors is you can substitute in V equals IR into that P equals IV formula and get these other two. But with those, it's a similar thing to like with capacitors of, okay, does power dissipation go up or down if you increase resistance? It depends on what else you're keeping fixed or letting change. So if voltage is fixed, the easiest to use this one. It doesn't mess you up on the trend. It says that a higher resistance decreases the power dissipated. If it's a fixed current, that one's going to be easier to work with because it tells you that the power dissipated increases if you're keeping current fixed and you raise resistance. But all three are technically valid at any time. It's just in the other versions of them, you may forget that multiple things are changing at once. Calculations of power. When we look at resistors in series and parallel, you see some more of those. So I'm going to gloss over those things. EMF, the definition of it, it's the work done per unit charge to increase a charge's potential energy. So how it does that is the electric field goes one way in a battery and our pretend positive charge is going to the other. And in order to do that, we are increasing the amount of energy it has to let it kind of go around the rest of the circuit to fall through the remaining potential difference, get back to zero potential. The internal resistance of that battery limits the amount of potential difference you can have across the battery's terminals, limits the amount of energy each charge has that moves through the circuit. And so we don't get the full, what we call EMF out of the battery. We don't get the full 12 volts out of the car battery. We get that minus whatever drop we have in electric potential due to the internal resistance of the battery. We may get 11.6 volts out of a car battery. We may get 11 volts. We may get even less. It depends on how much current is being drawn through that circuit. Like these two examples show. Excuse me. And so that's the main things for EMF is internal resistance, what EMF is, and that it's not going to be the same as the potential difference you get across the battery's terminals. Okay, loop rule and junction rule are mostly important in the sense of solving problems like this one a little bit later. This down here. So when you apply the loop and junction rules to solve a problem like this, my thinking at this point is that the type of questions you'd see are things like resistors in series and parallel, a question about a circuit sort of like this one, and it asked for a particular voltage or a particular current. And then I'll give you one more like this, where maybe we have multiple batteries, and so we can't use the series and parallel relationships. So you have to use Kirchhoff's rules. But if I do, I will be just asking you to set up the equations. You don't have to solve them, you just have to set them up. And to do that, you apply Kirchhoff's rules. Just follow that process. It will not lead you wrong. The only way you can mess things up is if you mess them up in this process. So just make sure it makes sense and follow it step by step, and you'll be okay. So because that's the main things for pure college rules, I'm going to say all the kind of lead up to it is not what you're being tested on. And similar for the junction rule, all the lead up to it is not what you're being tested on. It's can you apply it? Similar for resistors in series and parallel, you've just got a nice box that summarizes everything for you about them. The rest is just how do you get to those concepts? How do you get to those ideas for resistors in series and parallel? So applications are not being heavily tested on. That is not, it's mainly just what's in those boxes. So an example like this is good. And an example like, so application thing, an example like this one is very good. Very good one to look at. Okay, charging and discharging. The main things are, can you apply this formula to figure out how much charge is left in your capacitor after a certain amount of time if we're talking about discharging, or how much is on the capacitor if we're talking about charging. So this formula right here is if you're charging a capacitor, how much charge do you have it? When Q0 is the capacitance of the capacitor times the final potential difference across the battery potential difference, or battery voltage. And then for conceptual type questions, you can tell me things about the voltage and the current. That's important. I'm not worried about what is the current at any particular time. That's not as important as what is the charge. And then again, this stuff is just how do we get there. Time constant is important because it may say how long does it take to charge something. It's 5 of those. 5 time constants is our rule of thumb. Similar here, how we get there is not super important, but knowing how much charge is on there is, the trends in voltage and current, and then this example down here is a good example of that, and then there's a couple more on the front. Okay, so that is chapter 27, and so that's all 3 chapters. So maybe if I just do a quick, like, this, kind of thing, now that I've said more detail, it is, the biggest things are knowing the relationship between charge and voltage for capacitor. Knowing how to calculate parallel plate capacitance is most critical of all of those different types. Knowing what a dielectric does when you insert it to the capacitance and to the electric field. Knowing what it does to the charge or voltage, depending on if the other one is fixed or not. Looking at a circuit where you have capacitors in both series and parallel and telling me something about the charge on one of those capacitors or the voltage across it, or both, and the energy stored by it, which is this thing down here. Chapter 26, the biggies are relationship between current density and drift velocity. And can you use that to figure out how long it takes for charge to move through a certain circuit? It's always longer than you'd expect. It's on the order of usually minutes or hours for an electron to actually move through a circuit. The relationship between current and current density, the relationship between current and charge, that conventional current just does everything kind of the opposite of what's actually happening because we're so caught up in positive charge that we just pretend it's moving instead of the negative charge. How resistivity depends on temperature. How resistance depends on resistivity, as well as these other properties of a certain conductor or wire. That Ohm's law says resistance is constant. That's all it says. But that you can use this idea of resistance to relate voltage and current in circuits. Important. the power dissipated by a resistor in terms of either voltage or current is important. In chapter 27, it's not quite as much as it feels like, just based on the chapter. It's what is EMF? How does it differ from potential difference for a battery? The answer is the internal resistance drops what would have been available as energy for the charge to move through the circuit to a lower value, and that lower value is the potential difference we actually get across the terminals. EMF is the act of doing work to give something energy, but only some of that energy is actually left at the terminals of the battery because of the internal resistance of the battery. So that's why we talk about voltage or potential difference of a battery. It's what's left over to work with. It is the hill the charge has to fall down rather than what lifted it up. For Kirchhoff's rules, it's applying them to a particular circuit. And then for series and parallel resistors, it's again, can you find series or parallel or equivalent resistance if you've got multiple resistors? And then can you find the current through a certain resistor, the voltage across it, the power dissipated by it? That is just about it for RC circuits. Expect more conceptual questions. If you have a calculation one, it would be most likely related to time constants, how long it takes something to charge, and then how much charge you have. 1 second, Tiffany, let me just finish this last page. Discharging, similar questions. How long does it take to discharge? How much charge do you have after a certain amount of time? And then what do the voltage and current look like? Okay, Tiffany, what's your question?
You said the Kirchhoff rule, that's if it's not series or parallel, right? That's what you said.
Yeah, if it's not either, that's about your only option. So this example here is one case where you don't have series or parallel resistors. And so we have to apply Kirchhoff's rules. We do the junction rule first, look at currents entering and leaving junctions. We use that to label our resistors based on the direction the current flows. Conventional current always flows from high to low potential. That lets us label positive and negative here. And then we apply the loop rule to get a couple more equations. The loop rule is we follow each loop in the circuit around clockwise. We note whether we're going from positive to negative, which we call a drop in potential, or negative to positive, which we call a rise. And we use that to set up these equations of rises and drops. And for any resistors, we can replace that drop in potential with a current times a resistance. If we do that, we end up with enough equations to find all the currents going through this circuit, and that lets us find anything we care to find out about the circuit.
Okay, and that other one with the J, what is NE? Can you tell me what NE is?
Sure. So NE, scrolling back up here. There we go. So N is the number of charges per unit volume. Meaning I have 1 billion electrons per cubic meter of material is one example of N. In E, we multiply by the fundamental charge E, tells me how much charge I have per unit volume. And so if I had 1 billion electrons per unit volume, I would have 1 billion times 1.6 times 10 to the negative 19, whatever that number comes out to be, coulombs of charge per unit volume.
Okay.
Yeah, the current density then just says, okay, I have that amount of charge per unit volume moving through my circuit at this rate, at this drift velocity. So the current density relates the rate of motion, the velocity, to how much charge is actually flowing per second per volume.
Okay.
Well, I should say per area, but yeah. Okay, that is the note. So I'm going to jump to some practice problems. I do need to leave by about 3:45 today, so I'm going to try and get through as many practice problems as I can. Let's see how many that ends up being. but there was this question of number 46. So I will say how to set it up. I may not go through the whole thing. We've got an 8-volt battery right there, a 12-volt. We've got a 10-volt right here. It is, I should point out that it's going the other way. That could be relevant. What is the current in resistor 2? So what is I2? Is the current through that resistor? Okay, I'm given these values of resistance, and I need to solve this. I'm seeing multiple batteries. That's telling me I should look at Kirchhoff's. Okay, first thing I should do is just draw some currents based on the branches I see. And in my head, I see this first battery. I'm going to say this is I1. It's the current leaving that battery. If I drew it the other way around the circuit, there would be nothing wrong with that. That's just my choice. So this is I1. Okay, then I look at my 2 branches. Because this is a junction, I'm saying of 3 branches meeting. And I would say, okay, I should have a current going through this lower branch and going through the right branch. The directions I draw them also doesn't really matter. I can be wrong about this. So I'll call that I2 and I3. Okay, I now need to follow all of my currents to make sure I don't end up doing more work than I need to figure out what currents are what. So this I3, if I keep following it around, I'm going to see that it's eventually going to reach this bottom junction, because once it goes through this branch, it's only got that one way to go. There is no place for it to split off. Similar for I2, I'll draw it down this way. Okay, I guess I drew it the wrong way through my battery, but that's okay. We'll see if that's right or not. And then last for I1, I trace it back to that lower junction. Apparently it was leaving that lower junction. Okay, so I look at the junction rule. It says sum of currents entering, it's leaving. So I'll look at my top junction A. I could set it up for junction B as well, but I'm gonna get the same equation. I'll let you check that. I'm just gonna do A. So going into it, I see I1. Going out of it, I see I2 and I3. So that is my equation for a junction rule. Okay, now based on these currents, label positive and negative for my resistors. So I see I1 is going to the right for resistor 1, high to low. I always draw my positives and negatives to reflect that current should go high to low potential. Okay, now I2, this middle branch, positive to negative, and then I3, positive to negative, I4, positive to negative. The way that current is flowing through that resistor as I've drawn it. Okay, now loop rule. I look at my loops I see in my circuit. I see this one. I see this one. There is the outermost one that I could do as well, but in that case, I would get the same equation as if I added my 2 inner loops. So I usually just do the ones that I easily see, which are these 2 inner loops. Loop rule says, follow a loop around and see where you have rises in potential, where you go negative to positive, low to high, or we have drops where you go positive to negative, high to low. So around loop A, let's start with that, and then we'll go loop B. For loop A, I'm seeing, if I start at the bottom left corner, there is no reason for me to start in any particular place, but I just end up doing that a lot of the time. If I follow that around clockwise, the first thing I see is that battery, the 8-volt battery. I'm going negative to positive for it, so I call it a rise. Okay, I move on, I see R1, that resistor. I'm going positive to negative. I'm going to call that a drop of I1 R1. I keep going around my loop. I don't go off all the way into this other loop on the right side. I don't keep going that way. I make sure I continue around this loop that I've drawn. And so I go through this branch, I'm seeing now that I go from positive to negative. So that is another drop, I2, R2. I may then see my V2 battery. That is a battery with a 12-volt potential difference. Or no, that should be 18 is what it gave me. So that should be 18 volts. But I'm going high to low for that, positive to negative. So even though it's battery, I should call it a drop of 18 volts. And I'm just putting it over here because I'm kind of out. So 18 volts plus I1R1 plus I2R2. And if I keep going around that loop, I see there's nothing else. I'm back where I started eventually. So that's my first loop rule equation. For loop B, I do the same thing. I just start at some arbitrary point in the loop. Also, to start at the bottom left corner. No reason for that. I'm just rises and drops. So rises, I first encounter battery V2. I go negative to positive, so I do call it a rise, 18 volts. Then I see resistor R2, and going this direction, going in this loop, I should call that a rise as well. I go from negative to positive. Even though it is a resistor, if I'm following my loop B, I'm going from the negative to the positive terminal of that resistor. So I'm going to call it a rise of I2, R2. Keep following that loop around. I encounter resistor 3, R3, but I go positive to negative, so that's a drop. I keep going around and I see this 10-volt battery, but I go negative to positive, that's a rise. So I should give myself a little bit more space here. Rise of 10 volts. And finally, I encounter R4, and I'm going positive to negative on that terminal. So that's a drop. Plus I4, R4 is my drop in potential. So these are my three equations, and that would be where I call it a day as far as the exam goes. But you could then solve these for I1, I2, and I3. And if you did, maybe I got the directions right in the first place, maybe I didn't. If I didn't, I would get negative values for some of those currents. And that would tell me that I should have drawn, maybe if I1 comes out negative, I should have drawn it not going the way it's going, I should have drawn it going the other way. Or if it's I2, same deal there. So that's how Kirchhoff's rules problems go, and that works even if it's just a resistor network that you could use the series and parallel rules for, but instead you just decide you want to use Kirchhoff's rules to do it. Okay, so that's that question. What other questions are there? 20 minutes at this point. Looks like it's just you and me, Tiffany. Do you have other questions you want to look at?
Hold on, I'm looking at the exam right now. Hold on. Can you do number 16?
Okay, so copper contains 8.4 times 10 to the 28 free electrons per cubic meter. So this is that thing of charge I have per cubic meter, the number of charges I have. This would be what we call N. Copper wire of a certain cross-sectional area, so N, carries a current of 1 amp, so that's I. What is the electron drift speed? It's the D for that. Okay, so I see several things. I can't think of an equation that relates all of those simultaneously. But what I do know is that J, the current density, let's see, is that number N, the number of electrons per cubic meter, times the electron charge, the fundamental charge, times the drift velocity. So that, if I know the current density, will allow me to find the drift velocity because I know these two things already. E is just the fundamental charge from 1.6 to negative 19 coulombs. But I don't know my current density. So I have to stop and look at this again and say, huh, do I know any relationship between that and something else? I know how it relates to current and cross-sectional area. If it is a uniform current density, current is current density times area. So current density is current divided by area. If I put that in over here, I will get I over A is NE dV. Or if I solve for that drift speed, it's going to be I over NE A. So if I plug all of those things in that are given in the problem, that should get me to that drift speed. I won't do it just for the sake of time. So does that make sense, Tiffany?
Yeah, so okay, so the N, I'm still supposed to multiply by the 1.6 times 10 to the whatever.
Yeah, you can think of it like, okay, so I've got a certain mass of water flow. Okay, maybe I'm thinking of it as 10 boatloads of water, whatever a boatload of water is. To actually find the volume of water flowing, I need to multiply that number 10 by how much actual volume is in a boatload. Okay, I need to multiply by that boatload volume. That's like saying N times V will give me the total volume of water flow. It's a similar thing here. Sometimes this might be called like a number density N. To get the actual charge flowing, you need to multiply it by what the charge is.
No, I was getting confused because I thought like the 8.8 was NE already calculated type thing.
The 8.85 thing is epsilon 0.
No, 8.4 times 10 to the 28. I thought it was already multiplied.
I got you.
Yeah, you're saying electrons per cubic meter.
If you were given that something was coulombs per cubic meter, you had a certain number of coulombs of charge per cubic meter, that would be that you're already being given in E. So if you're just given number of electrons per cubic meter, that's in. But if they've told you how many coulombs per cubic meter, that is in E, because it's already accounted for the charge of each electron. Okay, what other questions?
That's it. I don't see nothing else because they don't have the ones like the homework with the doorknob and walking up and getting shocked and all this stuff.
So we got 15 minutes. Do you want to maybe pick one just to say, I haven't looked at it yet, but it looks like it might be tough if I try it later? Because you are in the hot seat because you are the, looks like, only one here. And that you get priority on what you want to know.
Do number 47.
Okay. An uncharged 5 microfarad capacitor, something like capacitance, and a resistor are connected in series. That might be relevant to a 12-volt battery. So that's something about voltage. And an open switch, maybe that's relevant to form a simple RC circuit. So at this point, I'd probably be drawing my circuit. I've got a capacitor. It's connected in series with a resistor. There is a switch. And there is a battery. which order I drew these things in doesn't matter. But it has a certain capacitance, certain resistance, has a switch, and then has a certain voltage. We close the switch at 0 seconds. The time constant is 4 seconds. So time constant, that's a thing labeled tau. We know it is resistance multiplied by capacitance. I don't know if that's helpful. It's just something I know. Determine the maximum charge on the capacitor. So it's asking for something about charge. Okay. If I close this switch on an uncharged capacitor, closing that switch is going to make charge start to flow from the battery around this circuit. It's going to charge up the capacitor. So this is a positive terminal, this is negative. This side of the capacitor is going to become positive, this side negative, and that's going to happen over time. We're going to build up more and more positive charge on the left plate and more negative on the right as positive charge leaves it. Still all using the idea of conventional current. So you'll have a current flowing for some amount of time. Okay, maximum charge. I don't necessarily know anything about maximum charge, but I do know that the charge over time for a charging capacitor. I look back at my sheet for a charging capacitor. I know that that is true. For Q0 is C times V0. I just got to remember that V0 is talking about the battery voltage, or in other words, it's the final potential difference across the capacitor plates. So those two things might be relevant for me to pull down. So Q01 minus E T over RC. And then Q0 is CT0. And so I just got to worry about maximum charge. It turns out that is this thing right here, because that is the final charge I end up with on my capacitor. But if I didn't remember that, I just knew something about this formula. I could also say, okay, the most charge I'm going to have is when this whole term is 0 as time goes out to infinity. That's going to make this thing right here 1. Otherwise, I'm subtracting something from it. I'm taking a little bit away. The most I could get out of this thing in parentheses is 1. And that's going to happen if the time becomes very large. It is when I get 1. But that leaves me with just that Q is Q0, that final charge on the plates. So that maximum charge is 5 microfarads. Can't remember micro, 10 to the negative 6, times the battery voltage, 12 volts. Turns out the time constant is not super critical to solve this, because this, whatever I get here, is going to be the answer. But I could look at it in terms of that time constant as well, by remembering that full charge happens after about 5 time constants. And so that's 20 seconds, since one time constant is 4 seconds. So I could instead put in 20 seconds for this time t, and 4 seconds for this time constant. And that will get me pretty much the correct answer. It's that idea of this gets me to 99.2%, I think it is, of my maximum charge. But to me, that's a perfectly valid solution as well. And so you could look at it as that was useful to know that time constant, if that's the way you want to approach the problem. Okay, other ones.
Yeah, do the next one after that one. 48.
Okay, what is the charge on either plate after one time constant has elapsed? So it's still asking me something about charge after one time constant. So C equals Q0, 1 minus E negative T over RC is still telling me something about time constants, or it's still telling me something about charge. And then what I could do is either just put in, okay, I know this is my time constant, 4 seconds, and it's saying after one of those, so put 4 seconds here as well. what do I get for that charge? And so it'll be Q0 to 1 minus E to the negative 4 seconds, 4 seconds, Q0 minus E, that's negative 1, or that should get you to about 0.632 Q0. And so from this previous problem, we know Q0, and so we just put it in. Alternatively, we could remember this is sort of the definition of a time constant. It is the how much time passes in order for there to be 63.2% of the final charge sitting on the capacitor. That's just in the notes, it's the definition. Or let's see, if you just forgot everything about time constants other than that you should take your resistance, multiply by your capacitance. Oh, I guess it didn't give you the resistor value. It didn't give you the resistance. So that would not be an option. You would kind of have to remember that this whole thing is your time constant, RC. Okay. So got about 6 minutes. Are there any other questions on this?
Can you go over number 3? I'm kind of confused about how the dielectric constants affects the plates, if it's parallel or series or whatever. I don't know.
So if we increase the dielectric constant between the plates, what happens to the capacitance? One way to do that is to start with an empty capacitor, and then you add in a slab of dielectric. What is dielectric? It's just any insulating material. It could be a stack of paper. It could be like a whole ream of copy paper that you just put in between the plates if the plates are far enough apart. It could be you put a certain type of oil or something in there. Just some sort of insulating material in between the plates. Okay, and then it's asking us, all right, if I have an increased dielectric constant, an increase in what we call permittivity between the plates, what happens to the capacitance? Well, we have to think about how the dielectric constant relates to the capacitance. There is a formula, epsilon 0A over D, that'll tell us that if this goes up, if dielectric constant goes up, capacitance goes up, and that tells me the answer is increases. Or I can get back down to like the bare bones physics of Y, and it's that idea of if I insert a dielectric, say this is positive, this is negative, that's going to induce a very slight negative charge on this face of my dielectric, and a very slight positive charge on this face. And because of that induced field, I start out with this original electric field between the two capacitor plates. The induced field from the dielectric leads to, it's an opposing electric field, the induced, the I. So the net electric field, what I end up with is something a little bit weaker than what I started with. This is E plus EI in terms of vectors, but the magnitudes is this, let's call this sorry, it's E0 for that initial value. So E0. What I end up with is E0 minus EI. The weaker electric field, that makes it easier to keep charge on these plates, to have it not pushed off from the charge that's already on the plates. And that means I'm better at storing charge now. I have a greater capacity to store charge. So that's sort of conceptual way. Yeah.
I had a question. I just don't understand why they always say parallel plates, and I'm always thinking about another capacitor.
You're thinking,
I mean,
theory?
when is a capacitor plate's not going to be parallel?
So for anything we've talked about, a cylindrical capacitor, technically those plates are parallel at all points on the surface. But it's really just specifying, in this case, two what you can imagine are rectangular plates at all times if you want, or it could be two circular plates, But the idea is that it's just sort of a planar situation. It's not cylindrical, it's not spherical. So anytime you see parallel plate capacitor, just think of two metal sheets placed side by side. That is an example of a parallel plate capacitor.
Okay, because yeah, I be trying to do two parallel capacitors, I guess.
Yeah, and that's a problem with the terminology. If we're doing questions of series and parallel, it probably would not double up on it. It would say two capacitors are in parallel. It may not say two parallel plate capacitors are in parallel. And the way it would avoid doing that is by giving you the values of capacitance, because that's not the focus there. It's probably finding an equivalent capacitance. So you don't usually see parallel in the sense of series and parallel, and then parallel plate capacitor happening at the same time in the question.
Okay, that's fine. I'm good. I'm gonna do the best I can. I don't know.
All right, yep, it's right at 3:45. So I'm gonna call it there anyway, but I'll see everyone on Tuesday. If you have questions, you can still email over the weekend, and I'll do my best to get back on those, including like, I still don't know how to solve so-and-so. There was a thing on the surveys about like solving all of these, and someday that'd be great. But in order for me to give detailed solutions to 48 different problems for each exam, it's going to take a little bit of time on my part, which has not been around this semester. Okay, so yeah, email if you have questions over the weekend to anyone, and I'll see you all on Tuesday for the exam.
All right, bye.